In video 2 of lesson 7, we're going to explore limits at infinity. Video 1 did infinite limits. So we're going to explore limits at infinity in order to be able to tell between the two conditions. And recall from pre-calculus when we talked about end behavior. And so that's what this first exercise is about, is talking about end behavior. So let's go through a few of these together, and we'll see where we're at. So the first one says limit as x approaches infinity, and what we have here is a polynomial. So from our experience with polynomials, we know we have end behavior based on the highest degree and the sign of the leading coefficient. So for us, the highest degree is going to be 4, so we have a 4th degree polynomial with a positive leading coefficient. So if you recall, that means our end behavior is going to look like this. So that means that this is an unbounded function. So as x approaches infinity, the function increases without bounds. Okay, so letter B, we also have a polynomial, and we are now going to negative infinity, but we'll look again at the end behavior. So we have a 3rd degree polynomial. So let me just first write this here. I didn't actually write what the limit was. Okay, we have a 3rd degree polynomial. With a positive leading coefficient. So our end behavior looks like this. So we're headed to negative infinity. So as, again, this will be unbounded. So as x approaches negative infinity, the function decreases without bounds. So that means our limit is going to be negative infinity. Okay, the third one is a rational expression, and what we want to notice is the fact that the degree of the numerator and denominator is the same, so it's going to be the ratio of the leading coefficients. So let me just sketch that down, the reasoning. So the degree of the numerator equals the degree of the denominator so there's a horizontal asymptote, and it's the ratio of the leading coefficients. So in this case, it's going to be y equals the 3 of the x squared in the numerator over the 1 in the denominator. So we get a limit of 3. Okay, finally in letter D, we have another rational function. This time we are going towards very small x's. We're going to negative infinity, and our degree in our denominator is larger than the degree in the numerator. So we have a horizontal asymptote that is 0. So let me just write that down. So the degree of the denominator is greater than the degree of the numerator. So there's a horizontal asymptote of y equals 0. So our function is headed to 0. So hopefully you remember that from last year. So we only have 4 different outcomes when you look at the behavior to the extrema left and right, so very large x or very small x. So in part A, the curves can increase without bounds like polynomial, and I have a parabola there in the picture, and so it's going to positive infinity. So what this is saying is, as x increases without bound, y increases without bound. Okay, the second one is as we go to negative x's, and we can decrease without bound. So in letter B, our function values are going to decrease without bound. So as x decreases without bound, y decreases without bound. That's what we're saying here. Okay, our other 2 possibilities is we can have asymptotic behavior. So as the curve can become asymptotic to the x-axis. So as x increases to infinity, what we see is the function is decreasing to a horizontal asymptote. So as x increases to infinity, y is headed to 0. And that goes the other way too. Even though it doesn't show like the actual limit notation, the picture is the same though. As x decreases that way, the y is going to head towards that asymptote as well. So this is headed to 0, or it could be a specific y value besides 0. So here we have a horizontal asymptote right along there, and so what we see is that in this case it's going to head towards some constant, and in this case it's going to be 3. And so as x increases to infinity, y is going to go towards 3 in this picture, and it's the same in the other direction as well. Okay, so those are the only 4 things that can happen as x increases. So how do we rationalize this in calculus? How do we use some calculus notation? So we know how to find the horizontal asymptotes for rational functions. So how do we do that with a limit? So here is the calculus way of talking about this. So if the degree of the numerator is less than the degree of the denominator, the limit is 0. So we write the limit as x approaches positive or negative infinity of f of x equals 0. If the degree of the numerator is the same as the degree of the denominator, then we have the ratio of the leading coefficients. And so the limit as x approaches positive and negative infinity of f of x. So you have the coefficient of the numerator's highest power of the coefficients of the denominator's highest power. And then if the degree of the numerator is bigger than the degree of the denominator, we have an unbounded function. So the function could head towards positive and negative infinity as x approaches positive or negative infinity. Okay, so we are going to see on the test that you might see limits in terms of an expression or a graph, and sometimes a table once in a while. So what we're supposed to do in this example is divide every term in a rational expression by the highest power of x that appears, and then apply the properties of limits to evaluate each piece. Okay, so for letter A, what this question is asking us to do is to divide by x squared, the highest power, in the denominator. And when we do that, we get this limit. The limit as x approaches infinity of 2 minus 10 over x divided by 1 minus 8 over x plus 15 over x squared. Okay, so now we can do direct substitution. And what we're going to find is 2 is 2. 10 over a very, very large number is going to be headed towards 0 because the power in the denominator is bigger. We have our 1 in the bottom, and minus another 0 because we have like 8 over 10 billion, super tiny number, and then plus 15 over 1 billion squared, which is also 0. So we get 2 over 1, which is 2. So as x goes to infinity, y heads to 2. So our limit as x goes to infinity of y is 2. And we can see that in the graph. We can see that as we trace this out, it's headed towards the horizontal asymptote. Okay, letter B. Same idea here. I'm going to divide by the highest power in the denominator. So I'm going to divide by x squared again. So I'm going to have the limit as x approaches infinity of 1 over x plus 3 over x squared. And in the denominator, we're going to have 1 plus 4 over x plus 5 over x squared. And we're going to do the same idea. And so in the top, we have 0 plus 0, because those denominators are going to get so large, those numbers are going to become super tiny, over 1 plus 0 plus 0. So we get 0 over 1, which is 0. So as x approaches infinity, y is going to approach 0. So our limit as x approaches infinity of the function is going to be 0. And again, we can see that we are headed to infinity. This is flattening out towards the x-axis. So what I'm going to do is I'm going to let you guys do the third one, and then I will put the answer here for you. Okay, so here's the answer for part C. Hopefully you remember how to find a slant asymptote. If you don't, you can ask in class tomorrow. So I am going to stop the video right here, and then in the next video we are going to finish up the last part. Actually, we only have one more page, so let's go ahead and finish. Okay, so what we have is we're supposed to summarize and discuss the characteristics that we have so far. So as x, so if we have a horizontal asymptote, and let's call that horizontal asymptote y equals b. And we know that b is going to be a real number. So what we're going to have is that our function is going to head towards that horizontal asymptote. Okay? So if we have a slant asymptote, the function, whether it's going to positive infinity or negative infinity, could be plus or minus infinity for both of these. And in case you didn't remember, and I'll say it now, you use long division to find the slant asymptote. Okay, so that's what happens if you have those types of asymptotes. Okay, so we have to be able to justify it using really good mathematics. So a mathematical statement that justifies all this is if the limit as x approaches infinity of f of x equals b, or the limit as x approaches negative infinity of f of x equals b, then y equals b is a horizontal asymptote. So we have to justify the horizontal asymptote by the behavior of the function. Okay. So I'm going to let you guys do this challenge exercise here and see if you can do it by algebraic techniques and not just looking at the graph. You can see what the answer is going to be from the graph, that we should get, as we approach negative infinity, it should be -3. As we approach infinity, it should be 3. So see if you can do that algebraically, and then we'll discuss it in class.